Okay, we're going to take a look at rational functions, and on your handout you were given number 1 has it says to graph f of x is equal to 1 over x, and to graph it on your graphing calculator. So let's come over here to the graphing calculator. I'm going to get my y equals, and I am going to put 1 divided by x. And I'm going to check my window because I was doing other stuff earlier. And I'm just going to go to a standard window. So select 6 in your zoom. And here is what our first rational function looks like. And this is a pretty typical looking rational function. Now on your handout you were asked what happens when f goes to infinity. What happens to the output? And so when f goes to infinity, my output, my f of x, or you can say y, goes to 0. And we can see this on the graph over here. As x gets very, 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 very large, my graph is approaching the horizontal intercept, or it's approaching 0. And then you're asked, as x goes to negative infinity, what does the output do? And here I would say y goes to, look over here, as x is getting very, very, very small, my output is going to 0 as well. And we might say, well, why is this happening? Well, if we look at the function here, when we have 1 over 1, that's 1. When we have 1 over 10, it's 1/10. When we have 1 over 100, it's 1/100th. And so as we increase our denominator, or as we divide by a larger and larger number, our output is going to be smaller and smaller and smaller, and that's why it's going to approach 0. Now, we can also look at the table here. We can go to our table, and let's say we do our table set at 0, but I'm going to go up by increments of, let's say, 10. And then I want to look at my table. Here again, as I see my x values grow, my y values are getting closer and closer and closer to 0. And that's true as I go to positive infinity, and it's also true, let me start my table set back at 0 and then go back into my table, and it's also true as we go to negative infinity, except we're approaching 0 on the negative side. Okay, so that's pretty much number 1. Let's look at number 2. This asks you to graph f of x is equal to 1 over x squared and see what's happening there. So I'm going to again go over to my graphing calculator, and I'm going to put 1 over x, and then I will have x squared. Enter. And then when I graph that, here I have something that looks like this. And this is typical for an x squared situation, because when you think about that, I'm squaring my denominator. So if I had a table of values, and let's say I go from -3 to 3, like we do so much of the time, and my f of x, I'm going to have 1 over -3 squared, or that's going to be 1/9. and then 1 over negative 2 squared, so it's going to be 1/4, and so on and so forth. Here, 1 over negative 1 squared, that would just give me 1. Now, here I have an interesting situation. I didn't discuss this in the first one, but we'll discuss it now. If I have this situation, if I have, kind of running out of room here, but 1 over 0, I have a problem here, okay? Because I cannot divide by 0. So when my denominator is 0, then the function is undefined at that point. So anytime I have a denominator and I've set that equal to 0, or it is 0, then the function is undefined. When the function is undefined, and I'll go get another color real quick. When the function is undefined, I actually have what we call a vertical asymptote. Okay, so right here I would have a vertical asymptote at x equals 0. Okay, so let's move on to number 3. Okay, for number 3, we have a little bit more going on here. We have a rational function, and it is equal to x over x squared minus 4. So here, the first thing that asks you to do is to evaluate g of 0. And so if I do that, I put 0 in for wherever I see x. And so I have 0 over negative 4, which is just equal to 0. So here I have my function at 0 is going to equal 0. So I'm just going to put, okay, at 0, it equals 0. So what is happening to the graph when x equals 0? Well, my output is 0 as well. Or it crosses my horizontal and vertical intercept are right there at the origin. Okay, the next question asks you, what happens if the denominator is equal to 0? Well, as I said before, when the denominator is equal to 0, when this part right here is equal to 0, then the function's going to be undefined, and we are going to have vertical asymptotes there. So what we can do is we can just take the denominator out, and we can to find the vertical asymptotes, we just set the denominator equal to 0. So here we can find the vertical asymptotes by setting the denominator equal to 0, and we're going to solve for this. So this should look very familiar into what we did when we were talking about quadratics. To solve for this, I would need to factor, and then I would say x plus 2 and x minus 2, set each one of these factors equal to 0, and solve for x. So I'm going to have x is equal to negative 2 and x is equal to 2. So then, now I know here at negative 2 and at 2, I am going to have vertical asymptotes. And sketch that in here. So to answer the next question that you have, what values of x would make the denominator equal to 0? It would be when x is equal to 2 and x is equal to negative 2. So again, to find that, we just set our denominator equal to 0 to find those vertical asymptotes. Now, cardinal rule is that your graph will not cross those vertical asymptotes because they're undefined at that point. Okay, let's look at the next question, which is what happens to the function when x approaches negative infinity. So here, again, if we look at the function, okay, we look at this up here. Let me get rid of some of this other stuff. So when x gets really, really big, what's going to happen to the output of this function? Well, we have to just think, we have to analyze this. As x gets really big, we would have kind of this negative 4, it really wouldn't matter. It'd become pretty insignificant pretty fast. And then we basically have x over x squared. And so as x gets really big, this x squared is going to overpower this x. So it would again kind of be the same situation where I have x over x times x. So it's kind of just like having 1 over x. And I saw before that as x got really large, the y value approached 0. So that's what's going to happen here as well. And as x approaches positive infinity, same thing, that the denominator is kind of going to overtake the numerator. I'm going to have more of a situation like this, so I'm going to have y approaches 0. And such it is true that whenever you have the degree of the numerator less than the degree of the denominator, then eventually your function is going to approach y equals 0. So if I had something like y is equal to x squared plus 3x plus 1 over x cubed minus 2x plus 3, when x gets really, really big, all of this stuff kind of just doesn't matter anymore because we're talking about really big numbers. So basically we would have x squared over x cubed, and again we could look at that as being x over x, x times x over x times x times x. So again, kind of ending up with that 1 over x situation. So this again is going to approach 0 when x is very, very big or when x is very, very small. Okay, so that wraps up number 3. And on part 2 of this, we will go ahead and explore, pick up on number 4 and keep exploring rational functions.